to MPIA. So let's welcome her.
Thank you very much for having me here again. It's been a long year for me. And today I'm going to introduce a survey called PHANGS. And PHANGS stand for Physics at High Angular Resolution in Nearby GalaxieS. And so far, this is the largest multi-wavelength survey of nearby galaxies with fast physical resolutions of about 100 parsec. And in this talk, I will introduce the motivation of the survey and the instrument or telescopes we use to conduct this multi-wavelength project, and the sample of this survey and the PHANGS team is a large team. And probably the most important two slides in this talk is the data products that we will release in the very near future from this month. In the second part of the talk, I will show you some preliminary results of molecular gas and star formation distributions seen by PHANGS. So the goal of PHANGS survey is to understand the interaction of small-scale star formations with large-scale galactic structures and galaxy evolutions. And this includes the physical properties of cold gas, especially the molecular gas, and the properties of star clusters, and the interaction between stars and gas, and that's the stellar feedback that drive mass and energy into the interstellar medium by like H2 regions and supernova. So this star formation process takes place in very small scale, less than 100 parsec. So observations with very high angular and physical resolution are required to resolve this process in nearby galaxies. On the other hand, there are many types of galaxies. For example, there are early type galaxies. They normally have small amount of cold gas, and the star formation efficiency of those gas is also low. Compared to late type galaxies, they are normally gas rich with high star formation efficiency. So the star formation may proceed differently in early type and late type galaxies. And the late type galaxies can be further classified into non-bar galaxies and bar galaxies. And their spiral arms can be classified into the grand design two-arm spirals or flocculent spirals. So these bar and spirals and other galactic structures may also dynamically affect the star formation process in galaxies. So to understand how star formation proceeds in galaxies, we need not only high resolution but also large sample size to include different types of galaxies. So here I'm going to show you some past efforts or surveys which try to understand star formations and gas properties in nearby galaxies. For the gas, there was like VLA SIMS survey map H1 in nearby galaxies, and NRO Atlas and Heracles Iran. They map CO molecular gas in nearby galaxies with single-dish telescopes. And then there is BIMA survey. They use BIMA to map interferometer to map molecular gas in nearby galaxies. And then now we have MPIA survey. They map dense gas tracers like Hsi-An, H0+, in nearby galaxies. And for star formations, there are SINS surveys and Kingfish surveys. They observe galaxies in mid to far infrared using Speeder and Herschel. So these surveys, they have relatively large sample size from 10 to several tens of galaxies, but they have relatively low physical resolutions from about sub-kpc to kp scale. So this is not enough to resolve star formation process in nearby galaxies. And before ALMA, the cloud scale molecular gas observations was restricted to those very nearby, was restricted to a single case studies, starting from those very nearby galaxies like LMC and SMC, and finally to somewhat distant galaxies like M51, but because it's very bright, so it's really easy to observe. And so here's the FANGS. FANGS will observe both molecular gas and star formation tracers at cloud scale resolutions in many nearby galaxies. So this is again a figure of the gas and star formation cycle. And we will we observe molecular gas with ALMA and star cluster with HST, and H2 regions and supernova permanent nebula with MUSE, VLT MUSE, IF MUSE spectroscopy, and HST. So this is the three main telescopes we use to conduct this multi-wavelength survey. And the H1 atomic gas, this is the component that we haven't explored in FANGS because mapping H1 in cloud scale in nearby galaxies is still very challenging and very time consuming. So we haven't considered H1 yet, but I think we will. And here I'm going to show you the sample size of FANGS. The first one is FANGS ALMA. FANGS ALMA is a ALMA large program led by Eva Schmidt. This project observed 74 nearby galaxies in CO221. And this is the original sample, but we decided to increase the sample size from 74 to 90 by including galaxies from the some FANGS ALMA pilot projects. So eventually the total number of galaxies is 90, and we will release 90 galaxies very soon. And for the FANGS MUSE, we have 19 galaxies. And both FANGS MUSE and FANGS ALMA are 100% completed, and the data reduction is almost complete. And FANGS HST observes 38 galaxies. So now you can see half of the ALMA sample do not have corresponding observations in star-forming tracers. And therefore, we have another survey called FANGS H-alpha, or FANGS narrowband H-alpha. This is narrowband, not IFU H-alpha observations for 68 galaxies using the MPG and DuPont telescopes. And this PHANGS HST just started last year, and PHANGS H alpha is also complete, 100% completed, and the data reduction and images also completed. And here's some selection criteria of PHANGS sample. And most of the PHANGS galaxies are lying on this star-forming length sequence, on this stellar mass, global stellar mass versus star formation rate line. But still, we have some so-called Green Valley galaxies and quiescent galaxies below the star-forming length sequence. And if you are interested in the PHANGS sample, you can download the sample table from the PHANGS website, and you can find the galaxy names and their distance, stellar mass, star formation rate, and the wavelengths that they have been observed with. So here I'm going to show you how the PHANGS ALMA map, CO map, compared to previous observations. So I use NGC 3627 as an example. So this is the single dish observation of these galaxies. And the physical resolution is about 700 parsec. And this map is dominated by 3 blocks, the center and the 2 bar ends. And this is the same galaxies observed with BIMA interferometers, and the physical resolution is 2 times higher. So we start to see some substructures along the bar and spiral arm. Okay. And this is the PHANGS ALMA map of these galaxies at 85 parsec resolutions. And you can see these knots break into many small giant molecular clouds or clumps. And also, ALMA detect many structures in the interarm regions and the faint regions. And we have this kind of map for 90 galaxies. And here's another example of the HST, the PHANGS HST image of this galaxy NGC 1559, and ALMA's CO map overlay on the HST in red color, and this is ALMA map of these galaxies. And the MUSE GRI composite image, MUSE line maps, and this one is interesting. This is the H2 region map. H2 regions of this galaxy color coded by metallicity of the H2 regions. So the PHANGS team, so far there are 83 members. It's a huge team. And these 83 members form 5 data working group. So the data working group are in charge of data reductions, data release, and multi-wavelength survey papers. And there are 5 science working groups. They are taking care of organizing our science idea and pushing us writing papers. So if you would like to use PHANGS data, or you have any science idea, please contact the please contact the working group lead. And we are very lucky that we have our 2020 FANGS team meeting just before the pandemic, at the end of January. And the FANGS team, so I put a name, I know you cannot read, but I put the names here. And the FANGS team, including former IAA student, OET. So that's the most important slides in this talk. That's the data product we are going to release in near futures. First of all, we will release the multi-wavelength images on the ALMA maps, including the data cube, moment 0, 1, 2, and their arrow maps will be released in the fall of this year, and very likely around Halloween, so that's 10 days from now. And the Muse and narrowband image will be released early next year, and it's TBD for HST because it's not completed yet. Observation is not completed yet. And then we will release some derived physical properties maps, like stellar mass maps and star formation rate maps. And we will release catalogs, many catalogs, like sample table catalog. It will include like the stellar mass and star formation rate measured by ourselves, the morphology classified by ourselves, and the total H2 and H1 mass, either from FANGS or from the archive. And we'll release giant molecular cloud catalog for more than 50 galaxies. This is made by Annie Hughes. And the catalog is already done. So it's at this stage of typing the papers. So the catalog should be able to release very soon. And then we have H2 region catalog. The H2 regions here are identified from VLT news, IFU data, but there are only 19 galaxies. And this is led by Francesco Santoro in MPIA. And then we will have H2 region catalog, not by IFU, but narrowband, for more than 50 galaxies. And this will be prepared by myself. And then we'll have star cluster catalog, made by Janice Lee. And then there are more. Other measurements, like pixel scale environmental mass. And so here's an example here. So the environment here means the galactic structures, like bulge or spiral arms, inner ring, circumnuclear ring. And so if you, like for example the mass here, the red regions are defined as spiral arms, and the white region is called inner disk, and the green region is bulge. So if you want to study, if you want to compare, for example, giant molecular cloud in the galactic centers and spiral arms, then you can use this mask to pick up the bulge regions and spiral arm regions. And then there will be pattern speed catalog for bar galaxies. CO and H alpha rotation curve. And this one is also done, but I don't know who will write the paper. And the mega table. The mega table is the table of radial gas and star formation properties. So if you are interested in the radial profile of, like, for example, star formation efficiency, then you can just use this mega table to make the plot. So you don't need to calculate the physical property at each ring by yourself. And here I'm going to show you some preliminary results of molecular gas and star formations distribution in nearby galaxies. And because it's very preliminary, so the comments on methodology, interpretations, and how to use such high resolution data are very welcome. So the goal of this paper is to probe the global property dependency of the relative distributions of molecular gas and star formation in nearby galaxies. And the global properties here means like stellar mass, global stellar mass, or morphology. And so, in other words, what we are going to do is compare the CO map and H2 region map. So I call it H2 region maps because the map we use, we have already removed the so-called diffuse ionized gas. So we call it H2 region maps. And the most direct or common way to compare CO and H alpha or other star formation tracer is calculating the molecular gas mass surface density from CO maps and the star formation rate surface density by H alpha maps or infrared maps. And many previous studies have shown that when the physical resolutions is low, like about 1 kiloparsec to whole galaxies, these two quantities, star formation rate surface density and molecular gas mass surface density are tightly correlated. And this is because, and this has been interpreted as molecular gas is indeed necessary for star formations. And star formation proceed in a similar way in different galaxies. And here are more examples of the tight correlation between gas mass and star formation rate surface density. And the main reasons for this tight correlation is because at these resolutions, KPC or lower, the map of molecular gas tracer, like CO map, and the map of star formation tracer, like H alpha map, are very similar. And the high resolution observations show more complex pictures. When the resolutions increase, like here, increase from right to left, the scatter of these relations become larger and larger. And this is because when the resolution approach to the scale of individual giant molecular cloud or individual star forming regions, then the tracer of molecular cloud and the tracer of star formations become spatially distinct. So here is an example. This is one of FRANC's galaxies, NGC 628, and here is the CO map and H alpha map of these galaxies at resolution of 47 parsec. And the right figure here shows the H2 region, identify H2 regions and giant molecular clouds in this rectangular region. So I put a scale bar here. This is 1 kiloparsec, and the resolution is 47 parsec. And you can see, well, there's no spatial correlations between molecular cloud and H2 regions at these resolutions. There are some giant molecular clouds they are not associated with any H2 regions, so they are not forming stars somehow. And there are many H2 regions they are not associated with giant molecular clouds. And although molecular cloud and H2 regions are still overlap in many regions, but the number of H2 regions per giant molecular cloud also still change from region to region. And this separation between molecular cloud, that is the x-axis of Kennicutt-Schmidt relations, and the H2 regions, that's the y-axis of the Kennicutt-Schmidt relations, contribute to the scatter of this relation.
Hsi-An, how much of the difference between H2 and the H2 can lead you to extinction?
Sorry, what's that mean?
I mean, extinction effect. When there is dense H2, you cannot see H2.
Yeah, that's possible. I don't have any number for how many H2 regions are missing now. But yes, I agree, that's possible. And within this presence or absence of gas and star formation tracer have some implications on the evolutionary stage of star formations, or the mechanism that trigger or inhibit star formations in ISM conditions. For example, imagine that there's a giant molecular cloud, and somehow it just not able to form star. So it stays in a state of giant molecular cloud longer than the normal molecular cloud. And if a gases is full of this kind of, we call it quiescent molecular cloud or quiescent gas, and if we observe these gases by ALMA and MUSE or VOT MUSE, then we will get many CO-only regions and no H-alpha emissions. And of course, this is an extreme case. And if some of these clouds can form star as expected, then we expect to see some H-alpha and CO overlap regions. Those are star-forming gas. And if the stellar feedback is strong and the paramolecular clouds or the surrounding clouds are dissolved, then we will see only H-alpha emissions in these regions and contributes from these massive star regions. Or if the molecular cloud at these regions are completely consumed by this star formation, then we will also see only H-alpha emission at these regions. So all this work is to constrain the constrain the global probability dependency of the gas and star formation distributions in nearby galaxies and examine the impact of the trend we observe, impact of resolution on the trend we observe. And we will use PHANGS alpha data and PHANGS narrowband H alpha data. Because we can also use PHANGS, but the sample size is too small, only 19 galaxies. So what we are going to do is very simple. The approach is very simple. We take the alpha CO map and then the narrowband H2 region map, and then we classify each pixel with significant emissions into CO only pixels or overlap pixels or H alpha only pixels. And the CO only pixels or regions represent quiescent gas, and the overlap regions is star forming gas, and the H alpha only region is region of massive stars only. And then for each galaxies, we calculate the fraction of satellites or pixels with CO and or H alpha emissions. So for example, this galaxy is IC 1954 at 150 parsec resolution. And this is the three category of the satellites. And in these galaxies, about 50% of pixels with emissions are H alpha only pixels or regions, and about 40% are star forming regions, and 50% are quiescent molecular gas. And this method has been applied to 8 galaxies by Eva Schmidt. This is a paper published last year. And they applied this approach to 8 galaxies. And this is the 8 galaxies. And most of the galaxies here are those, very nearby, large, spiral, typical galaxies, except for NGC 1568. And although they are very similar in terms of morphology, their satellite fractions are quite different. Like N51 is dominated by quiescent gases, and NGC 5068, this is the lowest mass gases in these 8 gases. Among these 8 gases, is dominated by H alpha only regions. And because there are only 8 galaxies here, so we were not able to perform any statistical analysis using these 8 galaxies. So we expand the sample size from 8 to 51 galaxies in this work. And it's interesting that we didn't detect any CO emissions in the galaxies IC 5332, even with ALMA. It's a nearby spiral galaxy. So we include these galaxies in our analysis because it represents the cold gas pool or molecular gas pool populations. So for these gases, it would have 0% of CO only and overlap regions and 100% of H alpha only regions. And we make this kind of, we call it sign-like map at 150 parsec resolution to 1.5 kilo parsec resolutions. But our main analysis will be performed at 150 parsec resolutions. And we will use other lower resolution maps to examine the impact of resolution. And here I show you the morphology and stellar mass of the 51 galaxies. So in fact, PHANGS doesn't have early type galaxies. So we don't have early type galaxies in the sample. And so the earliest type we have is S0. And the latest type we have is irregular galaxies. And the stellar mass range from about 10 to 9 to 10 to 11 solar mass. And here is another example of the very different sunlight fractions in the galaxies. Actually sorting them by something you can guess what it is. So first of all, we want to plot the sunlight fractions, different type of sunlight fractions, as a functions of galaxy morphology. So we use this T-type index to indicate the morphologies. So higher the number, later the morphology. And here's the results. So the x-axis just indicates which type of sunlight I'm plotting. Then the y-axis is the fractions of the sunlight I'm plotting. And for example, for the CO only sunlights, that's in blue color. Darker the color, later the morphology. I put the So the fraction of this quiescent nuclear gas decrease from early to late type gases. And the fractions of massive star regions increase from earlier to late type galaxies. And the fraction of star forming gas are similar for all types of gases. And we can also make the same plot but for stellar mass. So the as you may already know, the Hubble type morphology and stellar mass are somewhat correlated. The early type galaxies or earlier type galaxies tend to have higher stellar mass, and late type galaxies have lower stellar mass. So here's the results for stellar mass. And the trend we observe for Hubble type is reversed because stellar mass in Hubble type are anti-correlated. So the preliminary result is this present or absence of CO and H2 regions indeed depend on global galaxy properties like morphology and stellar mass. And so the star formations may indeed proceed in different ways in these galaxies. And we also check other global properties like inclinations or distance to make sure that this result is not driven by selection bias. And we also check whether these sign-like fractions are correlated with the sensitivity and resolutions of CO and HL5 observations. And they all show no correlations between those observational properties and the sunlight refraction. So we think the trend we see here are real. So, and here is the global fractions. So there's only one fraction for one galaxies. And the trend we see here are all preserved spatially or radially when we plot the radial sunlight fractions. So the next step is we want to know the physical origin of this trend. And maybe we can look into the ISM properties of these gases, like gas fractions or molecular gas fractions, or gas fraction compared to stellar mass, or molecular gas fractions compared to H1 mass. And there's a interesting thing, I think, to mention here is that this quiescent molecular gas, the surface density of this quiescent molecular gas are not necessarily low. So the surface density of this quiescent gas range from about 10 to more than 1,000 solar mass per parsec square. So their surface density is not that low, but somehow they do not form stars. So the physical properties of this quiescent molecular gas and the environment they are sitting in are very useful to constrain the mechanism that trigger or stop the star formations. And also this quiescent molecular gas, on average, they contribute 30% on average of the total molecular gas in the galaxies. So they are quite a lot. However, this interesting, I think, quiescent molecular gas, they are only visible in high resolution map. So here is the sunlight map for some galaxies at different resolution from 150 parsec to 1.5 kiloparsec. And as you can see, when we blur the image of CO and HL map to 1.5 kiloparsec resolutions, the galaxies are, except for this one, this is the one without CO detection. The galaxies are dominated by star-forming regions. And so to resolve this star formation process, or to study the star formation in nearby galaxies, I would say the minimum required physical resolutions is about 500 parsec, because when the resolution is lower than 500 parsec, we no longer see quiescent gas or massive star regions. And yeah. So here's a summary of the second part of the talk. But I think we have time, so I'll use this movie to summarize the first part of the talk. That's the PHANGS survey. And it's weird that there's no music for this movie. So we will study the cloud scale star formations in nearby galaxies to see the interplay between star formations and galactic structures and evolution. And this is PHANGS. And I store this figure. And we'll use our VLT, HST, the main telescopes. So the ALMA data will be released this month, 10 days from now. And the news will be early next year. And the HST is unknown yet. And that's the PHANGS website. So we'll put the updated information on the website. And that's the end. So I'll leave the summary here and take the questions. Thank you.
Question?
How different Hsi-An flashing is between like a 150 parsec, 200 parsec resolution?
100 parsec.
I mean, you mentioned about effect resolution. How different are those flashing are when you use different resolution?
Oh, I have a plot I didn't show. I have values here. So, like for the CO only, on average it was 40% at best resolutions we use, and then it will decrease to about 10 in 1.5 kpc resolutions. And H-alpha only is more complicated, but still you can see the decrease by on average about from 50% to 20%, and then these overlap regions increase from about 30% to 70% at lower resolutions. So then eventually, at the lowest resolutions, these overlap regions dominate the map, and that's why the Kennicutt-Schmidt relations is the scatter of the Kennicutt-Schmidt relation is small, because your CO map and H-alpha map become so similar, and this is true for all the galaxies.
So you have a selection criteria for those targets. So could you put that slide on the screen here?
So this is the initial selection criteria we put in the proposals. But the team is still calculating the stellar mass and star formation rate and the distance. In the survey paper, you may see some galaxies who has distance like 20 megaparsec or even further, and that is because we are still recalculating the distance and these two quantities. So this is just the initial criteria we put in the proposals.
Observation detect plus continuum?
I don't know, but I think no. I didn't read about this in the survey paper, so I guess maybe no.
Because personally, I'm still a little bit skeptical about using H-alphas.
Yeah.
This plus continuum has its own problem. If you have both, you can get a better picture.
Any other question?
I think you said that the fluctuation of COV and overlap and data only is different between different galaxies. So how about in the inside of galaxy? I mean, the fluctuation of the galaxy center region and the region is different.
Yes, we didn't. Yeah, I try to statistically quantify that using the environmental maps I mentioned. But still, the number of gases, even with PHANGS, is not large enough to do that.
Okay, so if no more question, then let's thank Hsi-An, okay?